Picture yourself driving beneath the ocean floor, millions of tons of seawater pressing down from above, while beneath your vehicle lies a seamless fusion of concrete and steel, assembled with precision measured in millimeters. This isn't science fiction, it's reality. Underwater tunnels representing one of humanity's most audacious engineering achievements. But constructing these colossal structures amid crushing water pressure, unstable sediments, and complete isolation from the surface demands solutions most people can't imagine. How did engineers turn the impossible into infrastructure hidden deep beneath the sea? Welcome to Macro Forge, where we explore the mega projects that challenge the limits of what's possible. If engineering that conquers the ocean depths fascinates you, hit subscribe. Let's discover how underwater tunnels get built in environments designed to destroy everything. In today's interconnected world, underwater tunnels revolutionized how nations move people and goods. These monumental structures unite lands once separated by vast oceans, mighty rivers, or deep bays, sparking transportation revolutions. Imagine traveling from one island to another or crossing a wide bay in minutes without ferries or towering bridges, all made possible by tunnels beneath the water. Beyond saving time, they sustain global commerce flow. Trade moves swiftly, safely, efficiently through underwater passages immune to weather conditions that ground ferries or damage bridges. For many nations, underwater tunnels became vital economic arteries, especially for port cities, unlocking opportunities for regional development that surface infrastructure simply cannot provide. But here's what most people don't realize. Building these requires preparation and design precision that makes surface construction look simple by comparison. Before engineers can excavate a single meter, they must understand what lies hidden beneath the ocean. The first phase involves comprehensive seabed surveys. Engineers study subsea topography using sonar mapping and seafloor imaging. They collect soil samples through deep core drilling. They analyze rock strata determining geological structure, bearing stability, and latent hazards that could doom construction. But it's not just about engineering. Environmental considerations get prioritized throughout planning. Project teams must assess potential impacts on marine ecosystems, species protection, habitat preservation, noise mitigation during construction. Some projects even install artificial reef structures, creating new marine habitats, compensating for construction disturbance. This survey phase can consume months or even years, but skipping it or rushing through means catastrophic failure when construction begins. Once engineers understand what they're working with, they face a critical decision. Which construction method will actually work in this specific environment? Then the real challenge begins. One of the most widely deployed techniques for underwater tunnel construction is the immersed tube method. The process starts not underwater, but on land. Massive reinforced concrete segments get prefabricated in controlled factory environments. Each standard element measures approximately 217 meters in length and weighs over 73,000 tons. Think about that scale. A single tunnel segment weighs more than most skyscrapers. These segments get manufactured with extreme precision, ensuring perfect alignment and watertight sealing once submerged. Inside each segment, multiple compartments serve specific functions. 2 main chambers for highway lanes, 1 for railway lines, another service corridor dedicated to future maintenance and inspection access. Once sections are complete, they face their most dangerous phase: transportation to sea, and careful lowering into pre-dredged positions on the seabed using floating pontoons and specialized cranes. Each segment gets joined sequentially, forming a continuous tunnel of required length. But here's where it gets terrifying. The most critical phase lies in joint connections. If seals aren't handled with absolute precision, seawater infiltration poses catastrophic risks. Engineers insert rubber gaskets between segments, ensuring watertightness. Layers of sand and gravel get placed above and around the tunnel, preventing buoyancy caused by water pressure. Only after connections are securely locked and stabilized do crews remove temporary end bulkheads, transforming individual tubes into seamless, watertight tunnels. However, this technique only works in areas with stable seabeds and gentle water currents. In environments with strong turbulence or complex underwater terrain, the immersed tube method becomes impractical anchoring difficulties, waterproof integrity challenges. Engineers need different solutions, and that's where the real technological marvel enters. The shield tunneling method, also known as tunnel boring machines, represents the pinnacle of modern tunnel construction technology. A TBM operates as a colossal self-contained system capable of excavating soil, collecting debris, and installing reinforced concrete tunnel linings simultaneously in a continuous closed-loop process. At the front lies a massive cutter head, nearly 12 meters in diameter, weighing over 200 tons. It's equipped with 140 high-strength steel cutting discs and blades rotating at approximately 2.7 revolutions per minute. As it spins, the cutter head exerts pressure up to 400 bar, enough force to crush compact rock and soil. Excavated material gets immediately drawn into the chamber behind the cutter head, where foam and water inject, maintaining earth pressure balance. This is essential, preventing collapse in soft or water-saturated ground. The slurry mixture travels via continuous conveyor belt to the surface, where it passes through discharge towers, gets mixed with lime-reducing moisture, then loaded onto trucks for disposal. But here's what makes this remarkable. As excavation progresses, the TBM's rear section automatically installs precast concrete segments, forming the tunnel lining. Once a full ring completes, grout injection systems fill gaps between lining and surrounding soil, securing the structure and ensuring it remains watertight. Afterward, hydraulic cylinders at the TBM rear push the entire machine forward, beginning the next cycle. Excavate, install, advance. Each cycle takes roughly 90 minutes, producing 8 to 10 lining rings daily, equivalent to approximately 20 meters of finished tunnel. Operating around the clock, hundreds of engineers monitor pressure, temperature, power systems, and real-time camera feeds, maintaining stability. Thanks to sealed and automated design, TBMs can operate for months underground without interruption. But there's a catch. Speed becomes the limitation. When encountering extremely hard rock or irregular pressure zones, engineers must extract the machine and switch to alternative methods. And that alternative is brutal. In areas with hard geological formations where tunnel boring machines can't operate effectively, engineers revert to the drill and blast method, a traditional yet still widely used technique demanding high precision and strict safety adherence. Unlike continuous TBM operation, this method proceeds in sequential cycles: drilling, blasting, mucking, supporting, reinforcing. The process begins with dozens of blast holes drilled into the tunnel face according to technical blueprints. Explosives in cartridge form get inserted deep into each borehole, fitted with electric detonators, connected by detonating cords arranged in groups controlling firing sequence. Each detonator gets timed, optimizing rock fragmentation while minimizing vibration and structural impact on surfaces above. All explosive materials are scanned, tested, certified safe before being brought underground. During preparation, ventilation fans and air ducts get disconnected and depressurized, preventing shockwave pressure from dislodging ventilation pipes. Before detonation, crews measure circuit resistance and thoroughly inspect all connections. Blasting only begins once every safety condition is verified. When the command issues, electrical signals trigger detonators, breaking approximately 1.5 meters of rock at the tunnel face. After each blast, work halts for at least 20 minutes, allowing inspection and ventilation. On average, each blast consumes between 80 and 100 kilograms of explosives, with 9 to 18 blasts conducted daily depending on geology and project scale. Although this method offers faster progress and lower costs, it produces intense vibrations that can crack structures and cause water leakage. That makes it unsuitable for underwater tunnels. Shockwaves severely impact marine life, so drill and blast technique gets primarily reserved for mountain tunnels or dry ground excavation, where TBM and immersed tube methods prove impractical. But when even these advanced methods fail, there's one final option. When geological conditions or high water pressure make TBMS or immersed tube methods impossible, engineers turn to traditional excavation. The process begins with constructing a main vertical shaft extending from surface down to tunnel level. This shaft serves as the project lifeline, transporting workers, machinery, materials, and excavated debris in and out of the site. Extracted soil and rock get drilled, loaded into sealed containers, hoisted to the surface by cranes for processing. In areas where blasting is prohibited or soil is too weak, crews switch to hydraulic cutting tools slicing through sediment layers. Although slower, this significantly reduces ground settlement risk and ensures tunnel stability. After each excavation phase, newly exposed sections get immediately reinforced with shotcrete, followed by steel arch installation, mesh reinforcements, rock bolts, and anchors preventing collapse and stabilizing structure. Mechanical and maintenance teams operate around the clock monitoring air pressure, equipment integrity, dewatering systems. Maintaining pressure equilibrium between tunnel interior and surrounding environment is the most critical factor. Any imbalance could allow seawater infiltration, flooding entire tunnel sections. By combining classical engineering principles with modern monitoring technologies, traditional excavation remains reliable for underwater tunnel projects in complex geological settings, where only persistence, precision, and deep understanding of marine pressure can ensure structural safety beneath the ocean floor. But construction is only half the battle. What happens after determines if these tunnels survive decades or fail catastrophically. After construction completes, the crucial phase begins: safety inspection and operational assessment. In many modern projects, both submerged and underground tunnels get designed with two levels, effectively doubling traffic capacity without expanding structural footprint. Drivers can maintain stable speeds around 60 kilometers per hour, while emergency exits position every 200 meters. Once structure is fully completed, engineers carry out rigorous testing series, waterproofing integrity verification, pressure resistance testing, fire safety assessment, heating and ventilation performance evaluation, overall structural stability confirmation. But the journey doesn't end when tunnels open. Maintenance truly determines longevity and safety. Dedicated technical teams conduct regular inspections of concrete lining, waterproof membranes, support frames, drainage systems, ensuring no deformation or cracking occurs over time. Hundreds of sensors installed throughout the tunnel continuously monitor pressure, temperature, humidity, vibration, transmitting real-time data to central control rooms where engineers can detect even earliest signs of structural fatigue. In parallel, cleaning and sediment removal get carried out periodically using specialized vehicles equipped with high-pressure water jets and suction systems, keeping tunnel floors clear and preventing blockages. Through combination of advanced sensor technology and precise manual maintenance routines, today's underwater tunnels can operate safely, efficiently, sustainably for decades, enduring harsh ocean depth environments while remaining testaments to human engineering resilience. China has constructed some of the world's longest and deepest underwater tunnels, pushing engineering boundaries that left Western observers stunned. Tunnels exceeding 5,000 meters in length, depths plunging over 40 meters beneath seabeds. Construction timelines that seemed impossible compressed through relentless 24-hour operations. The Jiaozhou Bay Tunnel connecting Qingdao spans nearly 8 kilometers, with sections over 60 meters below sea level. The Hong Kong-Zhuhai-Macau Bridge Tunnel extends nearly 7 kilometers through one of the world's busiest shipping lanes. These aren't just tunnels. They're underground highways carrying thousands of vehicles daily beneath crushing water pressure. American engineers studying these projects expressed genuine amazement at construction speed, precision, and scale. What took decades in other nations, China accomplished in years. The combination of massive labor forces, continuous operations, and technological integration created construction velocities previously thought impossible. But speed came with challenges: environmental concerns, safety questions, long-term maintenance uncertainties. Critics argue the rush to complete mega projects sometimes compromises careful engineering that ensures century-long lifespans. Supporters counter that China's tunnel network proves itself daily, moving millions safely while demonstrating engineering excellence. The debate continues, but the tunnels remain testament to what human determination and modern technology can achieve when combined at unprecedented scale. You've witnessed how underwater tunnels get constructed through methods ranging from immersed tube segments weighing 73,000 tons to tunnel boring machines crushing rock with 400 bar pressure to traditional excavation maintaining pressure equilibrium preventing catastrophic flooding. China's tunnels exceeding 5,000 meters in length through techniques that compressed decades into years, shocking observers worldwide. What impressed you most? The TBM technology, the immersed tube precision, the construction speed? Share your thoughts below. Thanks for watching Macro Forge, where we explore the engineering reshaping our world. See you in the next one.